So before the lunch break, we played with the RampFit software, which is a tool for fitting a ramp regression model to data. So we are in chapter 4, regression 1. That means regression against time, trend estimation. And let me now proceed first in these course slides, and then I think we do another exercise, or I think we now see what we did, and then we do it again with RampFit, and this time we do it with rating, and I will be slower to give you a chance to try it on your side. So I will go to the next slide. And we saw that, well, you have already the folder which contains RampFits and the data file and the RampFit software files and also the GNU-plot graphics viewer file. These are already inside. Then I gave you a link to the Windows command line zmd.exe. So this has been long been a Windows command. So I think it's rather convenient to work with the command line because you just type in with the keyboard, and you can use shortcuts and auto-completion and such things. I prefer that over working with the mouse. Okay, well, and you can design your Windows command line. That means how many, what is a buffer, how many lines it can store, and the colors and the size and so on. Then we use this the graphics viewer, and finally we ran RampFits by typing on the command line the words rampfitc.exe, and then we pressed enter, and then the software started. Then you watched me how I did the work with RampFit, and then we saw, well, as you can expect, you put in data file name, you see a plot of the series, and then some information field about the data, the spacing, maximum, minimum, and so on. And then we were in part 1, that means what I call detection, where we zoom on a time interval. And you can also go back to the original time interval. So for example, let me see whether, no, I have to do this. I beg your pardon, I'm not able to, it should work. I have problems with this, okay, I can't use this stuff at the moment. No problem, I do it without. Okay, anyhow, I have, you can see the mouse. Then you saw that I did what is called a smoothing, a k-nearest neighbor smoothing. This was just to have a rough look where the change points may be located. And then, well, we could also do this for the standard deviation. I will do this in a minute or so. And then we continued to the next part 2, which I call regression, where we prescribe the standard deviation. And we prescribed it in the first run as a constant, no weighting, constant weights unity. That means you use OLS for the ramp. Okay, but you could also impose a parametric form, and this is what we do in a minute. And then it was, although I have a fast machine, it was helpful for me to adjust the search grid where to look for the change point times. So I have to kind of narrow the search ranges, not over the full, but over a certain restricted range, because then computing is cheaper. Okay, this is what I did. Then we saw the plots of the RampFit and then the standard deviation and so on. And we could also have gone back to part 2 if things are not okay. And we will explore this way of working in the remainder of this course, because it is not just so that doing statistics means pressing the button and you get the result. You have to kind of fight for the truth. You have the data, but you have certain parameters to look at the data. The histogram bin width or the weighting and the search ranges. Excuse me. That is, it is you work in circles back and forth until you have a good selection of the parameters, and then you obtain then the final result. This is a way how I see applied statistical data analysis should be done. Okay, then I did it okay for the first run, and then we proceeded. And in part 3, we had a look at the residuals, data minus fit. These are the residuals, the numbers which represent the noise component. And the noise component, these numbers, they should look like what we assume. That means their distribution should be, well, it should be well behaved in a sense. That means not too skewed. If it would be very, very, very skewed, then one may have to think about other ways of estimation. It would lead us too far, but usually in climate sciences, some form of skewness is tolerable, because we can take that into account using the bootstrap. Okay, and then we saw the histogram and the leg one and the normal probability plot. That means a Gaussian distribution would plot as a straight line, which it roughly did. There was a mild form of right skewness, and then we plotted the residuals against time, and then the scatter plot to visualize persistence, and we used the persistence time estimation from chapter 2 to quantify persistence time. Okay, and this was this job of part 3, and we proceeded to part 4, bootstrap resampling, and based on the persistence time estimate and the Karlstein formula 328, we calculated the block length for the MBB, for the moving block bootstrap. Okay, 23 was the number of consecutive points we employed for resampling. 23 times average spacing. This is roughly then the length of the block for the bootstrap resampling. And this is certainly enough to capture the persistence. Then we put in the number of resamplings. Since time was short and I was a bit shy, I only put in 100. Well, regarding the number of resamplings, it depends a bit what type of uncertainty measure you wish to have. If you want to have a 99 or 95% percentile confidence interval, then you should have very many resamplings, 2,000 or maybe 5,000 or 10,000 even. On the other hand, here in this exercise, we just looked on the bootstrap standard error. That means the standard deviation of the replications. And for such purposes, a number of 400 or 200 or even 100 is also quite okay. So it's easier in a way to quantify the standard deviation, the bootstrap standard deviation, compared to estimating a high percentile confidence interval. Then we saw the counter and we saw the fit result, the parameter estimates, and also the bootstrap standard errors. And I alerted you as well that you can use RamFit also as an advanced tool for doing a linear regression, because, well, I think I will explain that later. It's easier to understand then if you watch me when I'm doing. Okay, and then we continued and wrote the output and exited and had lunch. We could as well have gone back to parts 1, 2, or 3. Okay, let me see what is the next. Okay. Now I would suggest jointly, so I will try to be slow, to do another modeling. And this time we studied the Arctic river runoffs, and in this time we use this plot here, panel B, with humans, with an increase of greenhouse gases, with an according rise in temperatures, and with an according increase of the hydrological cycle. And instead of what the authors, Pooh and others, 2005 in Geophysical Research Letters, a well-respected journal, but still one can improve. So we will fit another model, not two straight lines, but we fit what I call a break model. The task then is to not only determine these slopes and to show that the slope to what the more recent part is greater than the older part, but we also wish to quantify when did this change point happen. This is the idea of the analysis. I think this is also typically you get the data and you meditate over the data. You have some questions, you have some knowledge from the literature, you have some ideas what could be done. Could we try this more advanced stuff, or should we keep basic? And then you start and using the right tools to study in a quantitative manner what you are expecting or what you are curious about. Okay, so I will continue. And we have a look here at this break model. Okay, it has again 4 parameters, but it only has one change point, namely here T2. The level is x2. And we have a slope before and a slope later. You could as well, it's the same way of expressing it, say that the start of the interval you have a value of x1, and at the end you have a value of x3. So this is the figure, and this is the formula, okay? 4 parameters to be estimated. And we use again a weighted least squares estimation. That means data minus fit squared summed weighted. This should be minimized. It depends on 4 parameters. x1, x2, x3, this we get via the derivative, okay? We can take the derivative with respect to x1, x2, x3, and then set it equal to 0. Then we get 3 equations we can solve. The only thing we have to know is T2. And T2, as before with the ramp, we estimate in a brute force manner. That means we try all data points as candidate data points for the change point time. Maybe a comment here on the accuracy of the change point time estimates. I just explained you that we search T2 element of all time points. And if the time points are very coarsely resolved, large spacing, then also the solution is rather coarse. So my practical rejoinder to such a kind of criticism would be, it depends on what your uncertainties for T2 are. If these uncertainty, estimated by means of bootstrap resampling, if these uncertainties are larger than the spacing, then it doesn't matter, because they easily accommodate for the uncertainties, okay? And this is, by the way, what I usually have in practice. Hardly ever I've come across a situation where the spacing would not allow me to estimate such a change point. Okay, and also, because now we have just one parameter T2 and not 2, as with the ramp, fitting is now way more faster. Okay, so let me proceed now whether I have to do something else. No. So I'm now with this green box, and I will use here my notes, and I write down that I have to use the break-fit software. The data file we have looked at is now 1 minus 9b.txt, because this is a panel with the humans, okay? So I will now have to remove this stuff here, then I use where is it? Okay, and then I go to the course. Okay. Training workshops. And then we go to software. Okay, now we go to the other folder, the break-fit folder. And again, we see here the command line link on which I double click in a minute. For those of you who wish to study the source code, a Fortran source code, here it is. So you can use a text editor or another Fortran editor to make changes if you are confident to do this. And then you can rerun it. So Fortran is also, there exist many and also many good free compilers. A compiler is a software that generates, let me show you this stuff here. A compiler is a software that generates a computer software from the source code. Okay, now it has opened, so this is now a source code, just to give you an idea. So this Z here, this is a comment, okay? And then, well, this was done when I lived in Hanover. And then you see here, you have to document the software, because it is the same as with data. You have to document what you measure and what you program, so that others can understand what you did. Okay, and then you see different things, parameters to be done, and then some data. And this is the major part, okay? And then you see the different stuff here, the course version and so on. And you have some calculations to be done, and the routines, and then you use subroutines which do special tasks, and so a routine for random number generating, and so on. So I will now close that, and you can, with some experience, easily generate on your own machine software that runs. Usually my software runs on all the Windows machines, but for example, if you have a Mac or a Unix machine, then you would take the source code and look for a compiler, a Fortran compiler on a Mac or on a Unix, and then recompile the source for your machine. This is always the best if you compile it on your machine. Then it's kind of hardware and software are close together. Okay, now let me double click the command line, and then we run breakfit, then we run this stuff, and the data file is that one, okay? So I will now click here, now I double click. Okay, and then I'm again not happy with these, want to have it bigger, so I have to do this stuff. I think I had 28, and also the layout should be bigger. And I make it a bit in this direction. I'm still a bit new to this machine. It is such a, excuse me. Okay, now I'm here. Okay, now I'm slow. I press dir. This is a DOS command for letting us see what is inside. It is as before. We see the different files, and we now run breakfitc.exe. This goes by typing in breakfitc.exe. And now I press the enter button, and the software runs. I try to be slow to give you a chance to do it on your machine. Now, this is a paper from 2009. It was a kind of conference proceedings, so it was easy then to get this. Well, it's easier to publish a paper in a proceedings, because of course everyone wants that everything is published, so to say. Okay, I'm still happy with that paper. It's a European Physical Journal paper. Anyhow, now I type in the file name 1-9b.txt. Okay, so you imagine, or you recognize this thing here. Path means the folder and subfolders on your machine, and file name is, well, the name of the file. And since I copied the file into the same folder where the software resides, I do not have to repeat the full path. Okay? I will now press enter to run the software, and I have a look Okay. Okay. Now this is the software and the graphics. We see that we have on the vertical axis modeled runoff. I forgot at the moment the units. I think it's cubic kilometers per year. Anyhow. And on the horizontal is time till 2001. And we want to fit a line, a break model, here perhaps, and then it goes up there. And we can, without problems, do a full search. That means data are short, just 70 or so data points, and break fit is easier, faster to fit than ramp fit. We can make a full search. We don't have to narrow down the search ranges. I will now press enter to get rid of this plot. And now I'm here. I see that we have, or you see that we have 73 data points, and this is the interval. And these are the other numbers. Okay, now I will press Z to continue. Z and enter. And we come to the next field, regression. And you see that you have three options to do the weighting for the time-dependent variability function. And I will again set it as a constant equal to 1. There's no need to do a weighting. There's no reason to believe that some parts of the data are more accurately to be modeled than other regions. So in this case, for this exercise, I use the constant weighting. That means we use OLS, ordinary least squares, Z and enter. And now you are being asked about the number. Let me give a value of 7 and later I give a value of 1. This is just to tell you that we get the identical results, okay? That you don't, that we are confident. Okay, then we do the full search, 1929 and 2001. And we see already the fits, okay? Data in black. We have a full search, therefore these ranges from here to there. And this is the change point time. And in red is the fit curve. Okay, I will press enter now. And okay, you see, perhaps maybe variability was a bit higher here than there, but not so much. We could try to study whether this has an influence. Anyhow, we see that the change point is at 1974. And this is the thing we just keep in our mind. And I will now do another weighting. And we see also that this slope of 9.772. Maybe I write it down not to lose it. And the other slope is minus 1.061, 1974. I will now do another weighting. That means I use S here for the standard deviation. I see it again, I click it away by enter. I don't want to smooth it again, no, enter. Again, I prescribe a constant, C, enter. In this case, I use 1, enter. Fit is again here, standard deviation, and now we have the values. And we get the identical results. So as expected, it doesn't matter whether you use a weighting of 1 or 7, unless it is different from 0. Or,
Manfred,
yeah?
I'm really sorry, but can you be just a little bit slower?
Okay, yeah.
Thank you.
Who else is trying? You, Biljana?
Sorry?
Who else is trying to catch up with you?
Me, a lot of us, I think all
okay,
of
yeah.
Yes,
me too.
Thanks. No problem. I will go back to 1. And I press, I press Z to continue. And now we are again here with this standard deviation. So your task would now be to fit by OLS this break model, Z and 1, and then the search range. Okay? The time interval where to look for the change point. It is between 19, it is from there. The maximum interval you can take is from 1929 to 2001. Then you have it here. I press again enter. This plot shows the time-dependent standard deviation using a window that contains 10 points. Okay? It doesn't matter whether our fit value is here or there. We just assume it is a constant. For the numerical result, it doesn't play a role. I can also take 80. Let me do 80 again. I press enter to get rid of this. And I want to, and here in this part, I press S to change the weighting. Later I will continue by pressing Z, but I will press S again. S. So here's the S and enter. And again I see this plot, which I click away by pressing enter. And now I don't want to smooth, no. And now I'm being asked for the value and the shape of the curve of the standard deviation, and I take again a constant, Z. So here is what you can type in. Z, B, or R. You can also prescribe a break model or a ramp model for this time-dependent variability. I press a Z and enter. Now I'm being asked for the value of S. And now I will type in 80 or so. This is a fit per eye. This is a fit. It looks identical as before. It is unimpressed whether I put in 80, 7 or 1, as long as it is not 0. And now, okay, now it sits a bit nicer here, but this is just visually. It doesn't play a role so much. I press enter. So now I wait a bit and listen and look. Are you still? By the way, I recognize Xenia from Croatia. You were here a couple of years ago. You remember? Good, so you should now know what to do.
Actually, I forgot everything. Okay, but I will manage. Hi.
So you should give me a go-ahead, Biljana or the others, if I should continue.
Može? Okay, we can continue.
Yeah, good.
Yeah.
So I press Z. And now we see, well, as with the ramp, we study the residuals. And in this case, these are the weighted residuals, the Rs. Okay? And here is a histogram, the number of residuals that lie between, well, the minimum and that value and so on. And also you can imagine that for the histogram, I take again Scott's 1979 rule. So this is a minimum of the residuals, this is a maximum, then I take the sample standard deviation, and then this Scott equation. This gives me 5 bins. Okay, it may be Gaussian, maybe not Gaussian. It's difficult to make such a statement on a basis of data as few as 73. At least it's not so well behaved. It's not so badly behaved. Okay, let me press enter, and we now I think see the normal probability plot. Well, no big news. It is somehow straight. You should especially look here in the central part of the plots, and you can of course expect in the tails, the bigger values or the smaller values, there you may find smaller deviations of those. This is just reconfirming us that a Gaussian is difficult to reject as a model for these residuals. I press enter to continue, and now we see the variability, so to say visually. So these are the residuals, the weighted one against time. Okay, and it's difficult to say whether here the variability is smaller than there. Perhaps not. I have no idea. I did not try it hard to study this. I think it's not so important. I will press enter and see the next plot. And this is then the leg-1 scatter plot. Residual, current residual R of I against the preceding one, R of I minus 1. And there's a big cloud, I would say, of points. It's not clear whether there is any orientation here along this line. So I have to press the button and see the quantified persistence time. Okay, and here we are. The persistence time is 0.34, and the units are years. So this is maybe 3 months or so. This is not awfully long. Well, you have also to be in mind that the spacing is 1 year for this data set. Okay, and therefore it is not optimally designed for assessing very short persistence times. Okay, it would be better than to have monthly or daily data if your true persistence time is in the order of days or months. Yeah, and the equivalent or the correlation coefficient is also pretty small. And I would guess that if we do later the bootstrap, we will be suggested to have a block length of 1. That means there is no memory to be preserved. So I will press enter to continue, okay? Yeah. I will press Z to continue, Z, enter. And now I'm with the bootstrap. I could go back if I would not be happy, but I'm pretty happy. And I will do now the block bootstrap, B, and enter. And as I expected, 1 is the suggested Karlstein block length. Well, it is not only Karlstein. So in the book you find the references. Sherman and others kind of adapted the Karlstein formula for the MVP. Anyhow, you can also cite my book. It's not so awfully relevant, this stuff. So there's no reason to change this. So I press no and enter. Okay, now we see, I wonder why the hell I allowed 2 resamplings. I have no idea. It should be larger. With 2 you can't do anything. I do now 2000 because data are short, machine is fast, and the break is cheaper to fit than a ramp. 2000 and enter. And yeah, you see it runs. Maybe I get a map. Okay, and we are already here. Okay, we have now the change point time 1974. And this is a usual thing I look at, the standard deviation. Okay, I have now to study whether I should explain this stuff here. Well, let me postpone that a bit. This column here is what I call a robust standard deviation. And you see that the numbers are not so different. Whether it's 4 or 6 doesn't matter so much. I can explain, upon your request, later these robust standard deviation. But usually this is what I look at. These are the standard errors, that means the standard deviation over the replication, the bootstrap standard error, over for the fit values. This column here, this is the average over the 2000 fit values, which is very close to the fit. And also the median, the guy in the middle, is identical to the fit. This already shows you the fit is 1974, and the average or the median over the replication is also 1974. That means the bias is negligible. There's no reason to assume that there is a bias in the estimation. Okay, and then we have also good agreement. That means the fit agrees with the median or the average clearly within these uncertainty, the standard errors for the x2 value. This is the level of the change point. Then we have two slopes. This is an earlier slope, 1930 or so. It is negative, yes, it decreases over time, but the uncertainty is pretty large. It is 2, -1 plus or minus 2. That means it is not significantly different from 0. Okay, because it is the plus minus 1 sigma error does include the 0. This is an easy way to assess whether or not it is significantly different from 0. On the other hand, the more recent slope after 1974, we are at the value of 10 runoff units per year, and the uncertainty, well, it is either 2 or 3 or maybe 8, but I would say it is still significant. It is less than the value itself. You should also bear in mind that the data end in 2001. That means since 1974 we have 27 years. Therefore, the uncertainty for that slope estimate, we can expect that this uncertainty here is larger than that one, because here fewer data points contribute to this. Okay, now we come to a kind of a story. So usually when I teach here at home participants, and then I'm always very happy when I have participants from Holland, because then at this stage exactly I would ask them, what do you think, what happened in 1974? And then, well, if they are old enough, as old as me, then they will, okay, and then I tell all the other participants, this was when Germany won the World Cup against Holland in Munich. And, well, sometimes people are laughing, the Dutch people maybe not. Of course, since 2014, when the Germans flew out in Moscow very early, I'm not so loud here on this stuff anymore. Anyhow, this was maybe when I was a young boy and I watched then the Germans winning. Anyhow, it was 1974, and then we can, of course, not because of the football, but we can, of course, then look for other data sets. So I could imagine, for example, if we employ such a type of break-fit analysis for maybe runoff series or precipitation series from southeastern Europe, then it would be interesting to make maps where we plot this change point time, maybe with error bar somehow. It's a challenge how to plot it best. Then we can see whether or not there is a certain pattern that in some regions, maybe the coastal regions, the increase was earlier or later. I have no idea, but this is a way how to do some explorative statistics with the help of numbers. So that means we would look on trend and trend changes. Of course, can also take a temperature, precipitation, runoff, and such things. And also, Rob Wilby can use such models for quantifying the urbanization effects on temperature and or changes in the situation of precipitation measurement and such things. So these regression tools help also the data quality people. Okay, I could now, well, let me plot some bootstrap results. Let us just do a histogram of the 2000 change point times. So I will do B to plot the bootstrap result. And I can now use the change point time T2. That means I press here T2 and enter, so it reads the next 2 characters. And the second variable, I want to make a histogram. I don't want to make a scatter plot. Therefore, I do not want a second variable. No, NO and enter. And now we see the histogram. Okay? And the histogram over the replications, the bootstrap histogram, 2000 values. And we also see the median, which is 1974 when Germany won, okay? And hidden behind this median would be the fit value because it's identical value. Therefore, I can't see this, okay? And the horizontal distance from here to there, this would be what I call the robust standard deviation measure. Well, this was it's not a bad thing to employ robust tools. I will explain, let me explain that a bit later. And then I think it's easier than just speaking here. So this is an uncertainty measure. So I will get rid of the plot by pressing enter. And okay, we can also plot other things. I press B again, and then maybe X2, and again a histogram. Okay, there it is. We see some skewness to the right. In general, if you have a very strongly skewed error distribution or replications distribution, then you have to think about what measures are suitable for describing this, the mean or the median perhaps, and likely also this robust measure of the spread, how wide it is. Is this narrow or is it wide? Okay, I will press enter now, and now let us make a scatter plot for 2 variables, maybe T2 and X2, okay? T2, and now press X2. And now I see we see a scatter plot. On the vertical axis is X2, the replications, 2000, and on the horizontal is T2. And there is some orientation here, but not so awfully strong, I would say. Why do I report this? Well, because we learned that these uncertainty measures for the different parameters, they are also to some degree dependent on each other. Okay, so if T2 is pretty small, okay, somewhere here, then you hardly observe X2 values so big, then you are somewhere here. On the other hand, if your change point is pretty late, 1980 or 1990, then your X2 values would be more larger than smaller. So there's some orientation here, and one can, in principle, give such plots. However, hardly ever you have the space in a paper to make such plots. But maybe today, in the electronic age, where you can give hundreds of pages of supplementary material, you can put this on, of course. And you can also put it in technical reports or in maybe the students in their thesis. It is just the full information about the uncertainties, not only the sizes, but also how the different uncertainties are related to each other. Okay, let me now just try to do another fit of the standard deviation. So this is how I would typically do this. I will now slightly accelerate, not to lose contact with you, but to show you how you can interactively work. I will go back now. So first I have to go press Z to continue. And from this part 4, I will go back and maybe we study a different time interval. So I go back to the very first part, 1, and enter. And now I take a time interval. And now I want to say, well, let us study the older interval before Germany won the World Cup. Well, excuse me, we won it also in 1954, but let us take this. So I do 1929 and then 1974. So we start, it's just out of the blue that I try this one. Okay, just one. 1929, I forgot. Okay, so left boundary, 1921. Right boundary, 1974. Enter. Now it's difficult to spot anything, I would say. Maybe we had a downwards trend from the break fit, and I will try to let us fit a break now to this part. I would my expectation would be, well, we will certainly find somewhere a change point, but I would beg that the slopes before and after both are indistinguishable from 0. This is what I would expect if I look on the data and I also on the preceding result. So I use again a full search over the full interval and using OLS. I press Z to continue. And now with the rating, I impose again OLS, constant, variability, unity, Z for constant, 1 for unity, full search, 1929. Okay, maybe I show you now again a shortcut, because I already said humans are lazy, and maybe I'm especially human, especially lazy. Therefore, I programmed also here a method to make it easier. I can type in a very small number, 1 maybe, and then this automatically takes the minimum of the time interval, because 1 is less than 1929. And for the second, I take a very big number. Okay, and then I don't look up to the big number, I take then the maximum here. So this is what is automatically being done. Okay, and this is it already. We have here the change point time. We have here a slope which is pretty close to 0 by I. And then, of course, well, we see a downward trend here. And the change point time was 1957 or 8. This is 60, 58. And of course, the question now is that shown to be significantly different from 0? Does the bootstrap give us some clue here? I don't know. Let's see. Press enter. Ignore this. Press enter. Continue. The histogram won't tell us many new things. It is just 4 classes. Now it's really difficult to make something on this. At least you can't reject that it is well behaved. Okay, press enter. Also this difficult to reject that it is well behaved. Press enter. We see some variations here. Okay, maybe here smaller, but there's no reason to do a weighting in my view. And then we see a scatter plot. Also here, I see don't see a clear orientation. Okay, and now we see even a value of minus 999.999. Of course, tau is only defined for positive values. That means the numerical minimization tells me there is no solution for positive tau, and that means you can't distinguish tau from 0. Okay? That means there is no memory in the residuals at all. And the bootstrap again will employ a block length of unity. I press Z to continue. Okay, and now B for the bootstrap. And as I expected, block length is unity. I don't change this N for enter. And now again 2000. And we are done. Now the thing is, this is the first slope with a very, very large uncertainty. Okay, and now the second slope is minus 4.49. Okay, and now the question, well, it is also not significant. A bit worrying, if I see these numbers, is a huge difference between this one and that one. So I would have to go into the replications and look, are there outliers or very big values? Why is this so much bigger than that? Because if the distribution of these replications would be a normal distribution, then the value here, 1.84826 times this MAD, which stands for the median of absolute distances to the median. This is a measure of the spread. This is a robust measure of the spread. Robust means unaffected by the presence of outliers. Then, for a normal distribution, they should agree. They should be the same. And because they are so different, I would have to look into the data. But anyhow, even if I believe this to be more accurate, a better description of the uncertainty, 5.7 or so, which is still larger in absolute value than that one here. Okay? Therefore, they are not significantly different from 0. Okay? Therefore, as my expectation was, I would say, correct, you can't see many more things in these first part from 1929 to 1974. Okay, then maybe we play the same game from 1974 to the present. Okay, so again I go back, 1, enter. Now I press I again for the interval, I, enter. Left boundary 1974. Okay, and the right boundary I now give again a very big value because I'm lazy, and therefore it automatically brings me back to the maximum of the interval, to 2000 and something. Okay, 2001. Okay, this is now this sub-interval, just 28 points. It's really a challenge to fit a nonlinear model to so few data points. It is not very wise, so I just do it to demonstrate that nothing useful will come out of this. I continue, and again we use OLS. Z, enter, 1, this is a value, enter. Full search from very small to very big values, okay? This means again, these values 6 brings me to the minimum of the time interval, 1974, and this very, very, very big value brings me to the maximum, since I'm lazy. Okay, and this is now the fit, and we have a change point here at 1996. Evidently, if you would be a rather innocent science journalist or amateur blogger and you want to make a story, then you can take this data and then base all your claims on this change point. But this would be equivalent to completely ignoring the uncertainties. This is not what you in the project and as a respected researcher should do. You have to report the uncertainties because this prevents you from making overstatements. Okay? So let's check whether we find something. I'm pretty sure we don't find something. Okay, 3 classes, probability plot, residuals against time, scatter plot, hardly anything to be seen. Okay, in this case, tau is again 0.4, but doesn't matter so much. It's really very, very small, the persistence. Continue. And now we do the block bootstrap B and enter. Don't change this, this is okay, 2000. And we are done. And now we see, yeah, as expected. This is a slope here, the later slope, very steep, 38 something. But you see that the uncertainties here are clearly larger. Okay, maybe this one not so, but still one had to check this. But I'm pretty sure it would be way too dangerous to place any story on this ominous change point. The only series is, there is a, let me go back and do the final stuff. I go back, I take the full interval O and enter, full interval, then I continue Z enter, OLS, that means constant, unity, 1 enter, full search, very small, very big. We see the fits, press enter to continue, press enter. And then we do the residuals, we have to go through. Okay, then the bootstrap, no, 2000. Okay, and this was it. I think this is the only serious thing you can do. Yes, the colleagues, Pellivu and others, they were right in assuming that the inclusion of humans, the enhancement of the hydrological cycle, can be detected in the model output. Yeah, and these are the numbers. Hard, not significant before, and strongly upward and significant thereafter. This would be, so to say, the result of the statistical analysis. And now I will do the output, X and output. And you see here also then information about the different files that have been written as output files. Yeah, let me see. Or maybe are there questions on the software? Yeah. Let me see what else we have. I think I should go back to these. So this is what I did now. I did this, what I call break fitting. And here again is what I told you. I don't have to repeat this. And yeah, you just watched me doing this. I think now that the rest would be then, and we have to see what to do. You can, if you wish, repeat everything on the given data. You can use this or ramp it on own data if you have data and you would like to have it. An option would also be if I would be given data of your interest, then you would see how I would approach this. Of course, then we deal with issues of data format and such things. I could also proceed here and or go back to the lecture on the third technique on non-parametric regression, and it's up to you what you wish to have. Maybe I have a look in the chat whether I see something. Oh, there's nothing inside. You have to tell me.
Sorry, Manfred, can you again say it again? I was.
Yes, sir. We are here now. We ended now the breakfit tutorial, okay. And the question is how to proceed. I can analyze your data if you wish me. I have to somehow get access to. You can put it on the OneDrive. I can repeat things from the full day if you wish. If there are things that I was too fast about, or I should go more into details. It's a bit up to you, and I can also show you the third part, the regression, the non-parametric regression or the smoothing. It's a bit I'm involved in the project. I'm your servant, so you should let me know what I should do.
I think that we should ask everyone is it okay with them for you to continue with your own data and your own examples, or we can share some data, so we can put it in a chat maybe, or a link to the data. What I think maybe for this session we can continue with your examples, because we put some climate data on the OneDrive, but we didn't make it accessible to other people participating. So maybe we can go on with your examples, and then on the 5th day maybe somebody can use their own data if they are up to it. So
yeah, also the people can in the meantime send to me a data file. You can give different units or numbers. Of course I will treat this confidentially, so it would be a pleasure for me to show you. I have it usually here in the courses, and yeah. Okay, so let me now go back to the lecture first on the section 4.3 on the non-parametric regression, okay?
Okay.
I have to find out where it is. I think I go here. These are the slides, and yeah. So, okay. Let me see. I have to check why this stuff doesn't... I have no idea why my stick is not working. Okay, so I have to do the last one without the stick. No problem. So till now, we made models that contain parameters to describe the long-term change. That means a linear model is quite a simple model. Slope and intercept, just 2 parameters. It's easily solved in a nanosecond, as I told you. The first derivatives and then setting them equal to 0 and solving them. This is what your software package does. And now we will use a method to describe the trend without a parametric model. And the idea is as follows. We estimate the trend by averaging the points, the x of I, the small x, in a time neighborhood. Okay, not too far away, but also, yeah, we should have a certain number of points. The idea is that the short-term variations cancel out above and below, and the resulting trend appears. And as I told you, no parametric trend model is required. So this is also called smoothing this type. Okay, the curve gets smoother. This is the idea of this estimation. And some of you perhaps have worked with a technique called running mean smoothing. Is anyone aware of this? Just raise your hand. So, good. Well, you not. This is all. Yeah, Kale, great. Thanks. So the idea is to use a window. So this is time. This is X, data points in black, the window in blue. The window is shifted along the time axis. The window has a width of h, small h. This is a bandwidth. The units are time units, years for example. And the running mean, when you have 1, 2, 3, 4, 5 points, would calculate the mean over those 5 points. And the central time point would show this mean value. Then the window is moved, 1. This point comes in, this goes. Then the mean is recalculated. And this goes then to the new central time point, and so on. So it's always the average over those here. So mathematically speaking, we do not exactly the same, but what is very similar to this expression here. This is equation 4.52. It's clear. We have now a couple of hours today. Perhaps we are exhausted. So let me walk you again through this. So we are interested in the trend, X trend. We do an estimation based on data, therefore the heads. The index PC stands for Preisley and Chow. At least Preisley is I think both are very famous statisticians who presented this way of estimation. Now, the crucial thing is this function here. This is called the kernel function, cap k. It has an argument, t minus t of I. So t is where we want to know the trend value, and t of I is where our time values sit. Okay? And this difference we scale, we divide by h. And this is a blue curve. Okay? So this is a general expression. And in case of the blue curve here, this rectangular window, or you also call this a uniform kernel, the kernel outside that would have a value of 0, the values do simply not count, and inside they have a constant weight. Okay? This would be then the value of the kernel inside. And this is then attached to each data point. And the other things are then just normalization to get an estimate. Okay? And this is the bandwidth, h. And some examples of how a Gaussian may look like. It is not always advisable. Well, it's easier to sell. It gives a nicer curve at least if your window is not a uniform kernel here, but it is a smooth kernel. For example, a Gaussian kernel. This is a plot. This is the function. Or an inverted parabolic formula. This is a plot. And this is the kernel. It is also called an Epernechnikov kernel. Why is that easier? Well, if you go to this, back to the formula, if the kernel is a smooth function, that means without bends and jumps, then the estimate as well is a smooth function. And smooth is easier to sell. It doesn't matter so much. It's more for cosmetic reasons. Whether we take a Gaussian or a uniform, but at least it's easier to sell your papers. It is advisable. And sometimes it also has computational advantages to calculate, for example, using a Gaussian kernel, or also the Epernechnikov kernel. I think in the software uses this kernel I have for you. But now we deal with the fundamental problem. And we met this problem already in the morning, namely the selection of the bandwidth, the smoothing problem. If we have, let me go back and illustrate it. Let us assume we have a very small bandwidth, maybe just 2 or 3 data points, so to say, or a value of h that corresponds on average to 2 or 3 data points. This is more precisely. Then we would have few points inside. That means the estimate based on the number inside would have a pretty large statistical error, okay, or larger variance. On the other hand, such a small window is able to trace the shorter term variations, okay? On the other hand, a large window means more points inside, a reduced statistical error, but we lose the ability for resolving faster variations. Okay, so this is then a kind of a systematic error. And therefore, the smoothing problem is a trade-off problem between bias and standard error. A large bandwidth means a large bias but a small standard error, and the other way around. The choice which function to take, uniform or Gaussian, is more of a cosmetic interest. Not unimportant, but this is a fundamental problem. And we had that problem, similar problem also in density estimation. And there exist sometimes mathematical guidelines for solving this smoothing problem, which also I sometimes consider, but in my view, it is way more important to play with the bandwidth, to do some very moderate smoothing and then a stronger smoothing, and then look on the results and look what is significant. Are there many, many wiggles that can be seen using a small bands? Are they really there? And the bootstrap uncertainty bands help to assess this. So this is again a method to approach the truth, the true trend, and the parameter to adjust is the bandwidth. Okay. And now we do, let's have a look at another tool, which is called the running median. Okay, this is the same data points as before. Okay, and the median now is a point in the middle. Here we have 1, 2, 3, 4, 5 points. Number 3 is in the middle, and this is, it has this value, and the assigned time value is the central of the central point. Okay, then again this comes in, this goes away, and so on. So why should one think about using the median? So our project is called EXtremeClimTwin. So we are dealing also with extremes, and Jana Silman will explain more about extremes. But this is a way to detect extremes. So my question, it is more a rhetorical question. What would happen if that point here would not be here, but way more up? My computer is too small. It could be very, 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 very large value. How would the red point change? Or would it change? So anyone who claims that there would be a change raises her or his hand. Right. Everyone is quite perfect. It would not change. You're completely right. Yes, it is not impressed, this guy in the middle, whether the biggest one is there or there or there. It is still the guy in the middle. Therefore, such a trend estimate based on the median is a robust measure of the trend. It is unaffected by the presence of outliers. And in chapter 6 of the book, and maybe in the lecture of Jana Silman, the first thing with climate extremes is detection. If you have a time series and you wonder, well, which are the extremes, then you have to somehow impose detection criteria and employ detection parameters. And this is, in my experience, how the width of that window, also for extremes detection, and then the factor of, well, what threshold do you place? It would lead us too far here, but be aware that also you can also use a robust measure, not only of the trend, that means the median instead of the mean, but you can also calculate what is being called the MAD, the median of absolute distances to the median. This again would not be influenced by the presence of extremes. And these are therefore robust and suitable detection parameters for extremes. Okay, then we look here shortly on this sentence. Bickel, this is from Encyclopedia of Statistical Sciences. That means a real statistician. He defines a robust tool method, performs well also if the assumptions, the model assumptions, are somehow violated, the departure from the ideal. Very often the departure regards departures from the Gaussian shape, skewness, and so on. And a robust tool should then also yield results that are useful. They are not completely invalidated. I'm a bit unhappy that in the research literature, since a couple of decades now, the word robust is very strongly abused. It means, in the meaning of many of my colleagues, they want to say something nice about the data. It's accurate, it is large, and we have tested it and so on. But in statistical science, it has a clear meaning. That means the method works well also if the assumptions are violated. And perhaps we keep that in mind when we write our papers for the project. Okay, now the example, and I will I have the time then to show the software for doing this. These are now data from Germany, and these are kilo years. So this is from 0 kilo years, and we are a bit, yeah, okay. The first thing, and we go back 9 or so kilo years. Okay, kilo years age. First, now we speak about just a couple of thousand years back in time. That means we have to think about what is present. What does an age of 0 mean? So this depends on, so to say, on the community which which is, so to say, responsible for the data. So in this uranium, thorium, speleothem dating community, present is usually AD 1950 or AD 2000. And it is very important to keep that in mind and to write in the research papers on the dating what is present. I'm pretty sure there exist many wrong statements in the research literature. The only reason is that the people confused what is present. And therefore you have to be really careful. So in the last years, the B2K definition has become fashionable. That means before 2000. Okay, so that means 2000 would be present, the year 2000, AD 2000. Okay, so we see this is time on the horizontal. On the vertical, we see 18O. 18O measured in stalagmites, calcium carbonate material from caves in Western Germany. And so this was done in collaboration with researchers from where I did my diploma thesis, University of Heidelberg, Institute of Environmental Physics. And these guys had then working relations with guys from Bochum University and who had access to the caves. And we had a bigger project, and therefore you can do cave monitoring and you can study temperature and precipitation and CO2 in the cave and such things. And then you can relate 18O in the drip water that feeds the stalagmites to the different climate variables. And this is often important for speleothem climate data where it is not a priori clear what you observe with your proxy. It is helpful to do cave monitoring. And then, of course, the hope is that what applies in the current interval also applies then in the past. But if you can't make this assumption, you are wrong at paleoclimatology. You have to do some assumptions, and I think all the sciences have to make assumptions. For example, let me make some excursions. We do a logic. A two-way logic, yes or no, or other ways. The natural numbers, the Peano axioms, these are mathematical axioms, or space, three-dimensional space, and such things. All these are very deeply made assumptions when we speak in a rational manner, and therefore they belong also to the set of made assumptions. Okay, and here the assumption is, we deal here with Western Germany temperatures in winter. And here to the bottom is cold, and here to the top is warm, as usual. And so we see here a cold interval. Anyone an idea what that could be 400 or 500 years back in time? Or 300? So this is called the Little Ice Age. Okay, so often people claim that Peter Bruegel the Elder made paintings of people ice skating in Holland, and because the weather was pretty cold then. Perhaps it is true that Bruegel painted because of that. Then we have also around this year, maybe 1,000 years ago or a bit more, what is called the medieval climate anomaly or medieval warm period. So it was warm again before 1,000 years. And this part here is then the most recent part. This is anthropogenically enhanced climate warming. And this full interval, well, is called the Holocene. Well, the Holocene started at around 11,000 years, so we see the major part of the later Holocene. Okay, and the data points are, well, just these small dots, and we have two caves, Bunker Cave and other cave, and from Bunker we have two stalagmites. One is Bunker 1, the blue one, and one is Bunker 4, the red one. Okay, and then the question was, what are the trends? Time-dependent variability and time-dependent trend in these values. And also we did the same for the green one, for the other cave, stalagmite AH1. And we wanted to look at longer-term changes. So in this case, we set the bandwidth equal to 250 years. So this here is a kernel function. It is a different from the thing from Preisler and Chow method. Let me give you later a paper of mine where it is better explained than I can do at the moment. So then we look on the standard errors. Okay, so the trends are, the solid lines, okay, this one here. And then we use moving block bootstrap, data minus non-parametric fit. And then we put this into tau s, persistence time estimation. And then we estimate persistence time, we do a bias correction. This translates into equivalent autocorrelation coefficient. And this then can be used using the Karlstein formula into a block length selector for the MBB. And therefore we can preserve shape and we can preserve persistence. And we get resamples, new data on which we reapply the Gasser-Müller smoothing with the same bandwidth of 250 years, and we do that 10,000 times, we get 10,000 curves, and at each time value we calculate the standard error. Okay? And in addition to the bootstrap, we also do simulations of the time scale. Okay, so this was then work done together with colleagues. I think it's Dennis Scholz and Dirk Hoffmann and Jens Vohlmeister. So these are colleagues who work on developing age models and doing dating. And because the time scale is not exact, this again is not the hobby horse of statisticians, uncertain time scales. But this is often the situation with paleoclimate people. And in this paper, 2012, published in Climate of the Past, you have a copy in your reading material, we looked on what is the effect of the timescale uncertainties on these non-parametric trend estimates. And the short message is, it is not very big. Okay, let me see whether there's more. No. Now we have half an hour. So I take first your immediate questions if someone raises her or his hand. No. I think I will show you how the method works, but I also wish to have some time for the reading material. Therefore, I do not spend so much time on the software, maybe 10 minutes or so, yeah? Okay, so I will have to do this stuff. I make this small. And okay, you should hear me. I get a bit of water. Now, we are here in the workshop, in the software, and this is now the last software we do an exercise with, the kernel. And it has a bit different file structure. Well, this is what I click on in a minute or so. This is a paper, and the software, this is a software. Okay, this one. This is a source code, Fortran 90, and this is another software made from the same source, but the task of that software, which I run first, is to estimate the persistence time on the residuals. And then I first run this, and then I note the persistence time, and then I do the full software, the kernel. The software reads the data. They are contained in that folder, okay? And this is a data file I will read in a second. Bunker 4, maybe I'll write this down. Okay. And then there's another folder called tau-est, and this software writes an output file into that folder, and in that folder there is the software for persistence time estimation. So by the way, you will also see then persistence time estimation. At least it is okay if you grab the essence of what I'm doing. If you repeat it and try, you will certainly be able to do it yourself, but I don't expect you at this late stage to directly do what I am doing now. So I will press now, I double click this one here. Okay, and I make this again bigger. And 110 was a good choice. Okay, and then I make it even the okay, then make it smaller. Oops. So I'm now in this folder, and I will first look what's inside data, and I will now use the mouse. This is again to make life easy. I mark with the left mouse button the text, and I use the right mouse button to copy the text into the what I call mouse clipboard, into the memory, so I don't have to type in the file name. Now I run kernel, and I press the tab key for auto-completion. Not this one, not the source code, this one. Now I'm happy, and I now press enter. And this is the software. And now I use the mouse and press the right mouse button to release what's stored. And this is a file, okay? Okay. The software is more powerful than I could explain here. It can also do what is called local smoothing. That means a time-dependent bandwidth. Would lead us too far here. So let us proceed with global smoothing, constant bandwidth, G, enter. And we put in by hand, okay, I forgot at the moment whether I have, excuse me, I have to, I forgot at the moment whether I have kilo years or years as units. So I will enter. Okay, I think I have kilo years, but yeah, it's kilo years. This is what I always forget. So I rerun this. Global 0.25 kilo years. This is 250 years. And now it is not very user interactive. It has already written into this subfolder the residuals. So I will now use, I go into this folder, changing, and now I run the software. This is from a 2002 paper of mine. It automatically reads what I put out. I think, yeah, I have to give the number of points, which is 1008. And then this is a cost function for estimation. The suitability of the AR1 model, which is quite okay. The reduction in this orientation of the cloud is quite okay. So the green one are the data, the red one are the white noise residuals, which are, I would say, rather white. And then we see some simulations. And then we see what is called a kernel density estimate of the persistence time. And in red is the estimate, and in the middle vertical green line is the median, which is very close. Again, no significant bias to expect. And this is here is then the result. Okay, 25 years. So I would, or 0.025 kilo years. This is what I would then need for the software. So I will go back one below. I'm typing CLS for clear screen. So excuse me, I'm a bit accelerating. I have to stay in time. So I will now run the kernel, auto-completion tab, enter. Now I release again what's here, the same data file. Global smoothing, same now. We deal with the trend. Again, it's more powerful than I have time to explain. You can also, this is interesting, study the first derivative against time. Then you would look for where are the changes very steep, up or down. Can also be done. You can even study the second derivative. But here, for this exercise, we give a 0 and enter. And now the global bandwidth, what we prescribed, 0.25 kilo years. And now what I estimated, 0.025 and enter. And now I'm being asked for the time interval. And usually, or very often, I take the original time interval, O, and enter. But it's still a powerful software. You can also kind of interpolate or output the trend estimate as an evenly spaced points, or you can also use a file which contains just the time values and output the trend at those time values. This would be, for example, interesting if you have another series against which you wish to compare your trend estimate. This can be done, okay? But here I will just press O, and then the software, not very spectacularly, terminates. It's finished. Let's go into the results folder. So let me go here to the Explorer, and this is result. And now, yeah, just a minute ago, this file has been written. And I will open that. No, not this stuff. Okay, now I make this a bit smaller. And perhaps change this stuff here. Okay, and you have then everything you need here. This is the header with the information data file and the estimation parameters. And then the description here, what you find in the different columns. Let me make it smaller again. And then you have the time, the estimate, the bandwidth, and so on. And you have everything you need, so to make the output. I would suggest that I go now to the reading material, or if you have questions on this stuff. We have now, I would like to spend some time, maybe 10 minutes or so on the reading material, therefore I think it's better. Is it okay? Okay, I will just do this.
Manfred, I have just one question.
Yeah.
In your book and in the reading material, there is actually step-by-step tutorial as you showed us here. Also, I think that you will also use the same data as here in the presentation. Am I correct?
Yeah.
So we can rerun the data if we like, and then we can ask questions on the 5th day, if it's okay with you.
Yeah, of course.
Okay, thank you.
Mm-hmm. So let me, in the remainder part of this day, open this reading material. And okay, we see that I brought you 3 papers, and maybe the first, let me first go on to this paper. This is a lengthy paper. Can I make this a bit bigger? Get rid of this. Yeah, it's a Reviews of Geophysics, so quite a good journal. It was not. It took a while to do the analysis and to get the paper through. And I had well some co-authors who helped me with the interpretation, but it was a rather technical big effort, because let me show you this stuff. I'm making this bigger now. This is more now paleoclimatology. Now we deal here with mega years, okay, millions of years. And the Cenozoic, the new animals, since the dinosaurs are maybe since 65 million years ago. So, okay, then Yucatan, the asteroid, and well, the big change came. And then we see here over time, and this is 1800, in benthic forams on the ocean, a very long-term decrease. So it got cooler. Okay, so this is a Cretaceous period, very warm and so on. And then we have different steps, and I quantified, or we quantified the different steps. For example, this is a very prominent, the Eocene Oligocene transition. This was when the Antarctica, the South Pole, got glaciated. South Pole, we have very high mountains, so we have bedrock. So it's way easier to build up an ice sheet. Okay, and then it was at around 34 million years in time. It was a big change, and you can quantify how big the change was. Okay, and then we today dealt with the northern hemisphere glaciation over there, and you see different things, different transitions. Okay, okay, and you see here the early Eocene climate optimum. Well, optimum in the sense that warm is good. Today we know that perhaps it's not so good to have so warm, but anyhow, this is how people described it. So let me just briefly, this is the idea of the paper, to quantify the full Cenozoic transitions, and then you see the data are described again, not again, they are described here. So this is a data file, and yeah, Biljana, regarding the data management plan, we have to think about how to do this, because this data, the data here, I downloaded from a paper, and then in the supplementary material, I gave also then the interval, for the interval I studied, I gave them the data. So that the idea is that authors can reproduce what I did, given the data and given the methods. Okay, so this is the data, and then I explained, okay, other data, and then I explained the methods. Okay, you know this already, the different models and the estimation and so. And let me see whether there is more. You see then weighting and such things, and then in the end, I would say this is then the paper is full of figures and tables for the different climate transitions. So these numbers here are the data numbers, ocean drilling program sites and so, and then we have the tables. You have that for all the different transitions. So it took me, I think, 3 years or so to finish everything. But I'm still quite happy with that paper. So let me. So it's if you are interested in paleoclimate, or you have people from paleoclimatology, perhaps it's interesting for them. Then let me go briefly to the paper I mentioned. This is a climate of the past stuff here. get rid of this. So the idea of that paper was to study the effects of dating errors on the non-parametric trends. And yeah, okay, with the two colleagues who work on speleothems as well. Okay, here you have an explanation of the errors, dating errors. And then, okay, then here, chapter 2 describes the dating points. And then, this is again more of relevance for paleo people, age depth curves. Okay, how to fit a model for the archive depth and archive age. And these are the models. And then the method is described as well. You can imagine that if I have written the book, therefore I can often just extract parts of the book and adopt it and fit it to the journal. So it's a long time to write a book, and don't expect that I'd make much money of the book. It's more that I can show to the others what can be done, and they invite me to join them on a paper or a project proposal. This is way more important, a better reason to have this one. Okay, and here we discuss, maybe this is interesting here to the right, let me make this bigger, because here you really see the effects of the dating errors, here to the right. This is the interval from 6.0 to 6.7 kiloyears before present. Data points are the small lines. The solid line is the, let me see whether I can use this stuff. No. The solid line is an estimated trend. And then you see the shaded interval. This is with timescale errors. And these, the lines you hopefully can see, these are the interval bounds without timescale errors. So the timescale errors effects are very, very small. Well, as expected, because the dating errors are in the order of maybe 10 or 50 or maybe 100 years, but the... Sorry?
I'm sorry, I'm speaking in Serbian, sorry.
Yeah, but the kernel bandwidth is 250 years. That means clearly larger than the timescale uncertainty. Therefore, we should expect that the effects are very small. And now we can quantify this. This is always reassuring. We have some idea, some expectation, but then it would be a step further to try to quantify somehow what we expect. And this worked well here. Okay, then let me show you finally the third paper. This is the most recent one. It's a review paper, Earth Science Reviews. This is maybe more interesting for you guys because it's more recent. And also the interval. It is more on the past 120 years or so. So we use this GISTEMP series. Some of you certainly have come across this series. So done by the guys from the NASA. Yeah, and we heard, I think Robert, who explained the global warming pause. This was maybe a story that came up in 2009, but it's politics. It is done by non-scientists who wish to send the message that global warming made a pause. And they selected beforehand the interval where this statement is not easy to reject. But as soon afterwards, we see more data points. And we are unabatedly rising in temperature. There is no global pause. There is no hiatus in global warming. This is rubbish. Okay, so this is a data set. Then again, I explained the different models. You know this. This is linear regression here. And this, you have seen the formulas. I directly, of course, use the same LaTeX formula. A linear model is not very suited in my view. And let me see, what do we have here? Okay, then these are the residuals. And the moving block bootstrap is explained. And here is a plot of different models that can be used. This is a ramp, this is a brake. There exist other models which perhaps are helpful. And here to the right is the brake model fit, and also shown that the histogram with 2000, yes, replications, okay. And it's still at around 1974, so there was really something out there. Okay, so at least we can quantify global warming accelerated. Here at around this interval, it got steeper. It was increasing before and it got steeper thereafter. It is clear. Okay? And then I made a new figure, this one here to the right. This explains the Gasser-Müller kernel quite well. So with colors and so on. So if you want to understand the kernel method, then don't try the Price-Lichow kernel and their paper. Consider looking on the figure in that paper, because this explains, so to say, the weighting in the kernel function. So this is the Epernechnikov kernel, okay? This then tells you how the thing is technically done. Sometimes it's interesting to study also the technical details. Okay, then we see the same data, but now fitted the kernel, non-parametric trend. And yes, indeed, there was a warmer years at around the Second World War, and then it decreased. But then, of course, you know that the data quality may be reduced in that time interval. It has something to do with how sea surface temperature was measured on ships. US ships, British ships, war years, evidently. The ships had something better to do than measure temperature. They had to do for the fighting. But anyhow, so the data quality may be reduced here. And I think people are still working on improving the best estimate, because there's just one number, global temperature, at around 1944, for example. And the thing is to get close to that true number, given the limited amount of data. Okay, then we had a discussion. Let me see whether, here I give some the suspected hiatus of global warming, and then the stories, it has something to do with Copenhagen and the climate skeptics. And okay, this is how politics go, it is not science. And then here, this is interesting, the upper plot, because this shows the slope. Okay? This is now also done with the kernel software, but this time I estimated the first derivative. That means the change of temperature over time, and this can also be time dependent. And the question is whether or not we are here at zero or differently from zero. And we see that we are always in the positive area, and here for a short time you can't distinguish it from zero, maybe here, but soon after we are increasing and increasing again. So this again reinforces the notion that global warming did not make a pause. Okay, and then I warned also the readers, maybe this is a good way to stop. You have some power as a researcher if you present statistical analysis. Namely, you can select the fit interval over which to present results. And you should clearly avoid to present that what you have preconceived as being true. You should really fight hard what is the best the data can deliver. And evidently, there's always a room for cheating, and we should tell our students not to cheat. Okay. Yeah, I think then this was the end of the lecture.